Hey everybody. I wanted to do a quick discussion of how you would work up your data for an analysis that began with a solid sample. So you weighed out a bit of coffee grounds and you're testing for how much caffeine is in it. Or this would apply also to the metals analysis we're doing in soil. So you weigh out some soil and you're testing for how much magnesium or calcium or whatever is in it. So you start with a solid sample, but at some point this extraction extracts the analyte of interest out into a liquid, and that is what we're analyzing. So there's a little bit of abstraction here from the original sample. We're not testing that sample, and we want to be able to discuss what was the concentration of that original sample, not just what was the concentration of the extract that we analyzed. So let's dive in. The place we want to start is actually on our Canvas page, right here. And I've actually worked out a document sort of telling you about this in the textbook. So you should go there, you should go down to solid sample concentration calculations, and you should get out that document. And the key here, so I'll talk through this just briefly, but you can read this at your own time. So the key here is to understand the process that you did to get to that sample that you analyzed. Um, so this is sort of a dummy analysis that we've worked out so we can understand then how the calculations might work. So first, we weighed out a sample. Okay. So then we performed some kind of extraction. We, added water to it, leached out whatever was in it into water, or we did something else. Then we don't, in our class, we haven't been doing this very often, but if that sample came out, you expect it to be even more concentrated than what you wanted or less concentrated than what you would in the range you would like, you have a chance to either dilute or concentrate that extract. So you could take that extract and take 1 ml of that and bring it up to 10 mils volume. That's a 10 times dilution. You could do that. Then you would analyze that a sample of that finely diluted thing. So then when our calculations are going in reverse, we've got our calibration curve, and we first use the calibration curve to calculate the concentration of the sample, or of the thing that we analyze. So I'm going to call that the analysis concentration. So the first step then would just be to multiply by any dilution factors. You can just use the M1V1 equation if you don't know what I mean by dilution factors, in order to get the original extract concentration. Then all you have to do to get from the extract concentration to the concentration in the sample, where the extract concentration is a parts per mass over volume. So parts per million or parts per billion mass over volume. Sample concentration is a parts per million or billion mass over mass, because it was a solid sample. So all you have to do is multiply by the extract volume, canceling out the bottom unit that's in volume, and divide by the sample mass, replacing it with, multiply by the extract volume. I don't know if I said that correctly a second ago. And then divide by the sample mass, replacing that unit on the bottom with a mass unit. So it's a mass over mass percentage in the sample concentration. And I've shown you one example of how this could work out. I'm imagining the thing you analyzed, after you ran it through the calibration curve, you got back that it was 5 milligrams per liter, 5 parts per million of lead. First thing you do is multiply it by a dilution factor. If you didn't perform any other dilutions, it's just times 1. You get the same thing, 5 milligrams per liter. Then if you take that milligrams per liter and you assume that this was extracted into a 50 milliliter volume, which is something that could easily be done, then 50 milliliters is 0.05 liters. That cancels the liters of solution from the bottom of this parts per million problem right here. Parts per million unit right here. So that gives us out the milligrams of lead in our extract. The 0.25 milligrams of lead then should be divided last by the sample mass. The sample mass, it tells us, was 2.012 grams of soil in that particular sample that was weighed out. So 0.25 milligrams divided by 0.002012 kilograms of soil, converting that grams into kilograms. and then you get a new part per million mass over mass, 124 milligrams of lead per kilogram of soil, or 124 parts per million lead in soil by mass. So that's the process. So I'm going to go to Excel now and show you how this would look in an Excel spreadsheet, for example, for your Soxhlet calculations. And I did steal one of your classmates' data for the start of this, the minor modification. So you can see if it's yours. Here we are. Yeah, so we're going to go to Excel. We're going to see how this would play out. So this is Soxhlet data. So first off, we analyze the standards, and 5 ppm gave us this area, and 10 ppm gave us this area. Soxhlet is an external standard, or the HPLC is an external standard, so there's no naphthalene in here. We're just reading the area count under the caffeine curve. So then 25 milligrams per liter gave this area, etc. So we're going to do a response factors calibration. So this is just the response divided by the concentration. And we got our response factors. We calculate the average of those. The RSD 8% is passing based on our acceptance criteria. And that's our average response factor. Then we use that average response factor. We analyze the IDPs and the blank and the unknown. And we use that caffeine area that was recovered divided by the average response factor to get us an analysis concentration. Now, this is the concentration of what we analyzed, which was in the little vials that were submitted. So we had originally we had made our standards with a unit of milligrams per liter, and I want to actually change that. So if you remember from our last video, hopefully you've watched it, we just need to make sure that there's a million, to be in parts per million, there's a million difference in size between the bottom unit and the top unit. The top unit is a million times smaller than the bottom unit. So since a liter of water weighs about a kilogram, a milligram is a million times smaller than a kilogram. Milligrams per liter is our mass or volume parts per million unit. And I'm going to make each of those 1,000 times smaller to make this calculation a little bit clearer. I'm going to make that a microgram per milliliter. So I took milligram down to microgram, and I took liter down to milliliter. So we still have a million times difference. A microgram is a millionth of a gram. So a microgram is a millionth of a milliliter. And so I'm going to write that in, since that's my concentration unit. I'm going to make sure and make a note that this concentration unit is micrograms per milliliter. So there we go. Now I'm going to apply my dilution factor. And it looks like I need to insert a column here of 1. So we didn't dilute any of these. We just did the extraction and we analyzed the extract. So I'm going to go ahead and just make it clear that although this was the analysis concentration, it's also the same as the concentration of the extract of the liquid that we extracted directly out of the coffee grounds. So this is equal to this times the dilution, which is just 1. Perfect. Drag that sucker down. I'm going to adjust my decimal places because I just get annoyed by so many decimal places. So there you go. So these are the concentrations of my extract. Now, these were the mass of sample that I weighed out. In the case of the unknown, it was literally coffee grounds. In the case of the blank, it was just sand. In the case of the IDPs, it was sand. So and the volume, so I extracted that mass. I added caffeine to it. So now I had a sample of sand with caffeine added to it. And I extracted the caffeine back out of it into 100 milliliters of water. So that many grams out into 100 milliliters of water. So the sample concentration then is it's as simple as what we said. You take this extraction, you multiply it by the milliliters. That cancels the milliliters. Notice it's micrograms per milliliter divided by milliliters, or times milliliters. So the milliliters cancel. Milliliters here cancels the milliliters there. And then divided by the grams of the sample. So I cancel the milliliters of extract from the bottom and I replace it with the grams of the sample. I hit enter, and this in milligrams per liter is, or I should say now that that's sample concentration. That is incorrect now, in micrograms per gram, because I have the micrograms of caffeine still on top, but I replaced the milliliters of solution on the bottom with grams of sample, and now it's in concentration of micrograms per grams, which is parts per million, mass over mass. Oops. So there we go. There's my concentrations in mass over mass in the soil. And now comes the kind of tricky part. What did we expect this to be? We intentionally added an amount of standard to make it sure that our extract would read back near 50 parts per million, near 50 micrograms per milliliter. So how do we get that to be an expected concentration in our sample in the end? And there are multiple ways to deal with this. Some people just go ahead and calculate percent recovery at the extract stage. So they would just insert here, say they all should have been 50, and we're going to calculate our percent recovery there. And you could also calculate your percent RSD based on that as well. And there's really nothing wrong with doing it that way. That's perfectly fine. But you still need to take it to the sample concentration stage, because at least for the coffee, that's the only real accurate information that you wanted, was what the concentration of caffeine was in the coffee grounds. So you can't just not do this part of the calculations. You can do the recovery of your IDPs here, but you still have to do the rest of the calculations, because that's the real ultimate information you wanted. You can also, some people go ahead and, because these ones, the sample itself didn't originally contain caffeine. It was just some sand and we added caffeine to it. So sometimes people put in a dummy mass of 2 for that and don't enter the precise mass. And make the calculations easier that way. I'm going to suggest to you another way that I think is just the most sort of straightforward way, is just figure out, based on these masses, how much each individual one should have calculated back to, or how much I would have expected it to calculate back to. So I'm going to quick show you how the expect down here, make this bold so that you can see where I'm at. I'm going to quick calculate what the expected calculation or concentration of the IDP should have been. So basically, let's remember, as always, let's remember what we did. We took 0.5 milliliters of our 10,000 part per million standard, and let's go ahead and call that micrograms per milliliter, micrograms of caffeine per milliliter of water. And we added that to our sand, right? That's what we did. So the calculation then shouldn't be that complicated. It should just be 0.5 milliliters times 10,000 micrograms per milliliter. And that's going to give us an answer out of half of 10,000, which is 5,000 micrograms of caffeine. We added 5,000 micrograms of caffeine to each of those soil samples. So if we wanted to know what the expected concentration would be, it would be equal to 5,000 divided by that mass, 5,000 micrograms per gram. And I've got to change this expected concentration up here to micrograms per gram. And then so my expected concentration now is 2,132 micrograms per gram, because I added 5,000 micrograms to 2.3455 grams. So it should have read back at this precise concentration. And that's pretty much straightforward. I can just bring that down, and then it'll calculate a new expected concentration based on the sample masses. And then percent recovery, I can just calculate here as equals sample concentration divided by expected concentration in percent form. And there you go. Notice the RSDs actually were calculated based on column C. It doesn't really matter. You can calculate it, the RSD here, based on the recoveries, or I mean, you should get basically the same number. The problem is here, the reason we didn't want to calculate the RSD of the whole thing based on sample concentration. Well, I mean, it should have worked out. I mean, because we used a different sample mass for everyone. So it made sense. You could use the RSD of the recovery here, or you could use the analysis concentration here, but you wouldn't actually want to do it there because it's based on a very different sample mass. So the concentration should be varying. The concentration should be varying on each one. But the ratio should be the same. So this should be calculated then off the recovery or off the analysis concentration in this case. I stumbled through that explanation, but hopefully that works reasonably enough. These shouldn't be the same in this case, so we wouldn't want to use the RSD to calculate their variance. They should be different because we weighed out a different amount of mass in each case. So you would want to calculate it based on something that should be identical, which is our extract concentration should be identical, or our percent recovery should be identical. And should get the same number whichever way you choose to calculate that, or your analysis concentration. So that's pretty much it. Hopefully that makes sense. And you can ask me if you have questions. Notice we did still calculate our sample concentration down here, but we of course didn't continue that out to do expected concentration because for an unknown, there is no expected concentration. So hope that helps.